Okay, let's come back to our class. So basically, for the last class, we have been talking about this sequence alignment problem. And basically, for this sequence alignment problem, we can give a good dynamical programming algorithm to solve this. And basically, for the algorithm, actually, the time and space complexity calls can be both of a big O of Mn. But actually, based on a little bit more observation here, we can clearly see, basically, we have been drawing this two-dimensional directed graph here. We can clearly see that the space complexity of this algorithm can be improved to the minimum of M and N. And actually, and of course, actually for this algorithm, the time complexity to be cautious is still O of M times N here, because actually we need to, basically, the space can be saved, but we basically need time to refresh the columns. When we go to the third column, basically based from the second and the third column, say, actually we basically, if we add a certain column, we need a cost of O of M here. And actually, we have this for N iterations. So although the space complexity is actually smaller, the time complexity is still O of Mn. But actually, the space complexity is what we need to focus on. And actually, a following question is that, this is only like computing the values. And you can clearly see that if we only want to have like a penalty, optimal penalty value, we can do this in this space complexity. But what if we want to recover an optimal alignment, basically like a path from corner to corner? Basically, we want to figure out like a best alignment, it's basically like this path finding problem. So any questions that if you have? Okay, so let's get into the details here. So let's think about what is like a good way that maybe we can think about this. So actually, maybe let's still first when we want to talk about this, we can base on some further observations that maybe we can see here. So observation one. So this is a directed graph that maybe we can actually think a little bit something that is a little bit different. That, for instance, denote Fij and Gij. So because if we want to actually recover such a path, maybe we want to need to take a close look at what is happening in the middle. So basically, we define like two functions to be actually to be the shortest path. For the f is actually from 0, 0 to ij. And the case for the g is actually from ij to mn, respectively. So I think one observation, basic observation first we are going to make is that basically we can, although we are saying that actually the Gij here is actually moving from ij to mn. So basically we can actually do this in kind of a reverse sense. That basically we can compute a Gij by actually reversing the edge. Basically reversing the edge orientations. And inverting the rows of ij and mn. So let me say, let me actually give an example about what this observation is. Let me see whether this can be continued in this page. Oh, good. Okay. So the observation that we are going to say here, for instance, assume that, assume that this is the ij that we are currently concerning with. The Fij is basically, it's basically like the optimal path, from 0, 0 to ij here. And this is actually relatively clear. So by definition, the value of Gij is basically, we want to consider, this is the ij point, and basically want to assume that, for instance, this is the optimal path to this. So basically, we want to figure out like an optimal path, from ij to mn. But maybe on the other hand, you can also, excuse me, you can also regard this, as a problem that maybe you can just erase all this. Basically, erase all these edges and basically are replaced with the reverse direction. So basically you can consider like this. So the values are still the same. Basically, these. I mean, all the edges on the rows and columns, they still have weight on delta. And basically for the diagonal edges, I mean, here, for instance, it is basically alpha, I think it's x2 y4, and this is alpha x2 y5, and this is alpha. I mean, let me write maybe here alpha x3 y4, and this alpha x3 y5. So you can still feel free to consider a graph like this, but you just reverse all the orders. I mean, from all the order of edges between ij and mn here, just compute the reverse order. I mean, having like in the original graph from this vertex to the corner to mn, it's just like, I mean, you are actually moving from mn to ij, but with this graph with all the corresponding edges reversed. So why is this the case? So we can say that this is true because and actually, there is a very strong symmetry, symmetry in this problem, and actually about symmetric argument. And actually, we can just looking. I mean, when we design this OPT, basically using dynamic programs, we are looking at the end of the string, and basically we are looking at the end of the string, whether I mean xi or yj they are matched, or maybe xi is a match, or maybe yj is a match. But on the other hand, we can also look at this in a kind of symmetric sense that we can look at the beginnings. We can look at the beginnings of xi until xm, and actually yj until yn. And actually, we are going to have similarly gij is actually going to be the minimum of alpha xi yj plus g I plus 1 j plus 1 delta, excuse me, delta plus g ij plus 1 and delta plus g I plus 1 g. So I guess this is just like a symmetric argument, and basically for solving a sequence alignment problem, you can also look at the beginning of the strings, and we get such kind of discussions here. So any questions about this observation? Okay, so this is the first observation that basically for this problem, and actually not only for this dynamic programming algorithm, but actually for a lot of problems, we have such kind of symmetry. I mean, you want to look at the structure of the optimal solution, but maybe you can look at the end, or maybe you can look at the beginning. I mean, this is basically a very specific case where we actually have this kind of a very strong symmetry here that actually we can reverse the bottom right corner of the graph and corresponding edges here. So why do we actually want to do this? And this is basically going on with the following observations. And actually, especially having both functions f and g, they are really convenient for us to make the corresponding discussions here. But basically for the observation 2 here, so for observation 2 here, the cost of the shortest path that uses Aj. That uses Aj. So I want to emphasize this. So basically, I mean, there can be a lot of maybe for instance, like this is a path, and maybe for instance, this is a path. I mean, there can be a lot of different paths, but I'm talking about the cost of the shortest path that uses a specific point. Using a specific point Ij, and actually the corresponding cost is just Fij plus Gij. This is quite, I think, just by the definition of both f and g's, because f and g's, they're actually defined as corresponding to the shortest path from 0, 0 to ij. And also for the g is actually the shortest path from ij to mn. So basically, as long as you have a shortest path, I mean, from 0, 0 to mn, actually, it passes a certain point ij here. And of course, the corresponding value is going to be fij plus gij. So this is the second observation that we make here. And I guess subsequently, we can have a third observation. So for the third observation here, also let's say that Q be an index that minimizes this value, the value of f q n over 2 plus g q n over 2. Then basically, I mean, based on the second observation, we know that the shortest path from 0 to n uses q of uses a point q of n over 2 here. Okay, so any questions about this observation 2 and 3 here? So basically, I mean, the way that we actually construct this shortest path is that still, I mean, the values are more. I mean, we at the beginning we want to have the value. So basically, roughly speaking, the idea is that we want to use the optimal values to recover the shortest path. I mean, a trick here that we are going to use is that, I mean, we can have these function values f and g here, and basically we can compute the function values. So the observation 3 here gives something very important that basically, I mean, if we have the capability to compute the optimal values of f and g, what is something that must be on the path? I mean, for instance, this n over 2 is something that maybe, for instance, we just look at the middle. So, I mean, for n over 2 here, I mean, we can correspondingly compute, I mean, different q's here. I mean, basically, we can just regard this, I mean, this f q n over 2, and also a plus g q n over 2 as a function of g. Oh, sorry, as a function of q here. So basically, I mean, let Q be the index that's minimize this, and we basically know, I mean, based on observation 2 here, the shortest path from 0, 0 to mn just need to use this point Q of n over 2. Because otherwise, I mean, if this Q, I mean, if it minimizes and the shortest path does not use this point, I mean, after all, I mean, you just consider like an arbitrarily shortest path. I mean, it after all is going to cut in the middle. I mean, I guess here probably in the middle, it's either like y2 or y3. It after all is going to actually transfer through the middle. I mean, this over 2 point. I mean, for instance, if it transfers at this point, I mean, and actually this Q does not minimize that. We just got a contradiction here. So that is actually a reason why we have this after having this observation 2, we must have the observation 3. So good. Any questions? Okay, so I guess from this perspective, you can clearly see, I mean, here, I mean, at the very beginning, I'm saying that probably for the sequence alignment problem, it's not that easy that you can directly solve this by a divide and conquer approach or maybe like a greedy approach. But here, actually, to recover the shortest path, we are actually using the idea of dynamic programs here. So basically, I mean, in general, for this sequence alignment problem, I mean, after I still need to introduce some technical details here. But the take-home message, mainly for the sequence alignment problem, is that on the one hand, I mean, for a lot of dynamic programming problem, the space complexity can be improved with like more clever observations here. And also on the other hand, and maybe along this line, I mean, there can be some uses of other algorithmic ideas. For instance, like divide and conquer. For instance, like greedy algorithm that can help us improve something. So here, actually, the main idea, as I just mentioned, is that we want to combine the dynamic programming. We just write DP here with divide and conquer. To recover the shortest path. And actually, in our case, I mean, the shortest path is just like the optimal sequence alignment in our problem, the scenario of our problem. So basically, this is our idea. So how do we actually do this? So basically, let's draw like this. Maybe let's just copy this here. So the intuition is just that we want to cut in the middle, and basically after cutting the middle, so for instance, this is like in the middle. Basically, we have both function f and g's. It suffices that after we do that, we just like regard this as two subproblems. Like one is this problem, basically on the upper left corner, and the other is basically this bottom right corner. So basically, we just want to consider things like this. So maybe let me actually put this in the middle. So basically, the idea is that we can apply a divide and conquer approach, roughly speaking, like that. So let's actually do this in a more formal kind of sense. So basically, for the divide part, basically, I mean, we are actually going to, based on observation 3 here, because observation 3 here clearly gives us basically at least one point that is going to lie on this shortest path, I mean, for our optimal sequence alignment. So for the divide part, we are going to find an index Q that minimizes F Qn over 2 plus G Qn over 2 using the original algorithm. Actually, I mean, we just do this. I mean, by using original algorithm, and actually, we have like a bracket here, which actually takes O of Mn time. But actually, I mean, here we just look at the perspective. I mean, as we just discussed, the space complexity is actually O of min of Mn here, but actually O of min Mn is of course Om here. Basically, this is the way of making a discussion that we only look at the columns. Surfaces that we look at in this kind of sense. And basically, I mean, even if we run this algorithm with only OM space complexity, actually the algorithm, I mean, the output, as I just mentioned, is actually we are always going to save the previous column and the current column. Because we are calculating the FQn over 2 here, and also the the GQn over 2 here. So both the algorithm is actually going to save the current column. So we can safely say that, I mean, basically for both, if we use the original algorithm, actually they are going to store this as F star n over 2 and G star n over 2 for all starting in. So basically, nevertheless, this is still something that is can be given by the original algorithm, because it actually saves the value of the last column. I mean, the last column here, I mean, if this value is n over 2 here, it's just like the n over 2 column in the original here. And basically, after having, I mean, after we find the index and minimize this value, we just, I mean, of course, the next thing that we are going to do, because based on the observation 3 here, we know that the point Q n over 2 is going to be a 1 point on the shortest path. We just output. I think line is more like a terminology here, but we just like a line. We say output this X Q by over 2 as like output of 1 point of this optimal sequence alignment. And in this, when we do the conquer, we just recursively compute optimal alignment in each piece. So any questions about this? Basically this idea, and basically based on the divide and conquer. So next we are going to analyze what is the cost of this algorithm based on divide and conquer. But I mean, do you have any questions about like the intuition of this? Okay, so let's then analyze the time and space complexity of this. So basically we denote, I mean, we use T for time, I mean, T and N, and S for space, to denote the time and space complexity. The writing is not so good. Space complexity of the algorithm. So how about time complexity first? I mean, as always, I mean, in a divide and conquer algorithm, we basically write recursions to represent the time complexities. So basically for this problem, we can clearly see, for this algorithm, we can clearly see that the time complexity of TMN is actually going to be smaller than the T of Q over 2 because we need to call the f function recursively. And also we need to plus like a T of n minus Q over 2 to call the second part of the function recursively. And actually, in calculation, in our calculation, we actually make a call to the original algorithm. So actually, the thing we need to, the other thing we need to plus here is basically O of Mn here. O of Mn for the this O is basically the cost of the original algorithm. And excuse me. So here, actually, I guess for our convenience, we just write this as capital C times Mn here. I mean, to just make things look clearly. Here, this here. I mean, here, note. The C is the constant in the big O of the original algorithm. So this is clearly a recursion that we are actually having here. So do you have any questions about this recursion of time complexity? So we prove the induction that actually we have T and M smaller than 2C times N. So this is clearly true when M equals to 2 or N equals to 2 here. So in our assumption, I guess in general, we can assume that M or N is actually at least 2 here. Because actually, if I'm at N, if actually one of them is actually at most 1, for instance, if M equals to 0, this problem, I mean, as the OPT suggests, I mean, if one of the value is 0, you just return I delta or J delta respectively. And if, for instance, M equals to 1 or J equals to 1, it is basically just a chain in this graph, and just like go through that. So that is actually, oh, sorry, I guess I'm probably, I guess I'm probably saying a little bit wrong here. Oh, I guess if M equals to 0 oh, I guess maybe here it should probably just be 0. I guess if M equals to 0, it's just the case that you just go through this chain. I mean, here the x1 here begins from the second the second row here, and y here begins from the second columns here. So if one of the values is just equals to 0, this is just a trivial case where you just have like for instance, just have the first column, or maybe for instance, just have the first row here. This just corresponds to the case where in the original algorithm, sorry, in the original like analysis, we know that these values are just I delta or J delta. So this is just trivial if M equals to 0 or N equals to 0. We actually don't pay any time complexity of that. So after having that, so now assume the correctness. Let's say, I mean, here we are assuming that we have making the induction for all the values smaller than M plus N. So for the current case, so I guess, let me write this clear. So for the current case, T of Mn is actually smaller than T of Q over 2 plus T of M minus Q over 2 plus C times Mn. And actually, I mean, we just call this we know we have by induction we have this. I mean, for all the values smaller than n plus n. So we just call this recursively, and we know that this like 2c times q times n over 2 plus 2c times like m minus q times n over 2 plus c times mn. And actually, we make a very brief calculation here. This actually equals to CQN, and actually this equals to C m minus Qn plus CMN, and actually this equals to 2C times n. And basically this finishes the induction. Okay, so any question about the analysis of the time complexity here? Okay, so I guess, I mean, this basically suggests that the overhead, I mean, by this divide and conquer algorithm is basically at most 2 here. So basically this does not influence the big O, basically the symptotic bound here. The very important thing, or the remaining thing that we need to do here is to analyze the space complexity of this divide and conquer idea. So basically, I mean, the first thing that we note is that, I mean, that basically finding the Q that minimizes Qn over 2 plus G. Qn over 2 actually takes OM space. Basically, computing for this is not a big problem because at the end of computing f and g here by the rational algorithm, we have stored the corresponding last columns of this problem, and basically just looking at the table, we just clearly just only take OM space to like compute the minimum of the of M entries among this. So this is not a big problem. So basically, we think about what is actually happening in this algorithm, and basically we need to what is the specific complexity that we need to be very careful about. So basically, we note that after finding the minimum, we can actually release the space. I mean, other than the aligning basically this value of xq yn over 2. That basically output this, which actually takes actually one space. And go to the recursive part. So the first thing that we actually do in this divide and conquer is that we call the original algorithm. Actually, call the original algorithm as we discussed. It takes the space complexity O of n. But after doing that, we can release the space, and we just like, I mean, other than storing this value of xq yn over 2 here, we store this taking one space, and then we go to the recursive part. And the remaining thing is that we need to be careful about what is the space complexity of the recursive. So for the second point is that we then recursively compute the shortest path. I mean, from 0, 0 to Qn over 2, which is going to take S Qn over 2 space. And the output, I mean, we are talking about the shortest path. So we think about, I mean, from 0, 0 to Qn over 2, I mean, we do, of course, we need to do this recursively. But what is the final output? The final output is the shortest path from 0, 0 to Qn over 2. And this path actually is going to have length of n over 2 here. So we say the output has length. Or we say actually it takes space n over 2 here. So we store this output and refresh other space. So this is the second point that we do here. So basically, if we want to give an algorithm with good space complexity, we can clearly see that maybe we want to be a little bit careful here, that we want to keep the best use of the space here. But nevertheless, because we need to output the final result here, so basically, very importantly, for the first point, we need to align the current point xq y over 2 here. And actually, for the second point here, we need to output the shortest path to solve the corresponding f. And of course, for the third point is that we need to work on the G part. So basically, we finally recursively, so we finally recursively compute. I mean, this is basically the reverse shortest path problem. That basically we consider the function G here, and basically we consider all like red edges like this in this reverse direction. But that is basically the same due to symmetry here. Nevertheless, we're going to consider like the reverse or shortest path from M n to Q n over 2 here. And actually, for this part, we can clearly see that by the definition of recursion, which actually takes as a minus Q n over 2 space and the output have n over 2. Okay, so those are basically the 3 steps of the algorithm that we can comprehend here. So maybe let's actually draw something a little bit more intuitive. So assume that this is basically like a space that we have to solve the problem. So step 1 here is basically take at most, OM space. Basically, we denote the constant. The constant in big O still as C here. So basically, this is the first step that we actually call the regional algorithm. So the next step, we just copy this here. So the next step that we are going to have is that actually we know or store the value of xq yn over 2 here. We actually delete one space here, and then we actually subsequently run the f part recursively, and this actually is going to take at most s q over 2 plus 1 space. And after having that, we then, excuse me. So basically, this part is actually the shortest path before xq yn over 2, which comes from the recursive call. And basically, we are going to use the rest of the space to finish the computation of the G part. So for step 3 here, actually it takes at most as m minus q n over 2 plus actually n over 2 for storing the shortest path before xq y over 2 plus 1 space for storing this value of xq y over 2 here. So therefore, a final conclusion that we can make for the recursive formula of the space complexities is that basically Smn is actually smaller than the maximum of C times M. So here we use the C here to represent the constant of the space complexity of the regional algorithm, actually smaller than the max of C times M as Qn over 2 plus 1, and also as M minus Qn over 2 plus n over 2 plus 1. So Smn is actually smaller than the maximum of these 3 true values. So any questions about these 3 points and actually the recursive formula that we get? Okay, so if there is no question, let's actually solve this. To solve this, actually, I mean, you can clearly see that this induction, this induction for the analysis of the time complexity, this is really transparent that, we know that like the constant part is actually like C times Mn, and basically we use induction to prove that this is actually smaller than 2C times Mn. So basically, for the maximum here, it is a little bit evolved here, but nevertheless, maybe we can use like a similar strategy here, still based on induction, and basically having a good guess about like what is the specific form here that we are actually using here. So here we say that we can use the induction. Basically, we prove by induction that Smn is actually smaller than C times M plus N. So basically, when m equals to 0 or n equals to 0, this is just trivial. Because when m equals to 0, n equals to 0, there is even no space complexity. We just know that the value is actually I delta, J delta. We just right after we know what is the value of m, and we just output the corresponding delta. M delta or n delta, which is just trivial. So basically, we know that for the constant case is actually trivial. So basically now assume the correctness when actually the value of m plus n is actually smaller than this, and actually and focus on the current case. Okay, so for the current case, we know that Smn is actually going to be smaller than the maximum of Cm. I'm just copying this down as Qn over 2 plus 1 as m minus Qn over 2 plus n over 2 plus 1. And actually for the 2 as in this maximum, we can just call this recursively, and it's smaller than max of Cm. Actually C times Q plus n over 2 plus 1, and actually C times m minus Q plus n over 2 plus n over 2 plus 1. And actually this is smaller than C times m plus n. So why is this the case? We can just do a quick sanity check here. So clearly Cm is smaller than C. To show like a value of something is smaller than an upper bound, it suffices that you show that each of them is smaller than this upper bound. So excuse me. So clearly Cm is actually smaller than C times m plus n. And also actually C times Q plus n over 2 plus 1. The m here is actually at most 1, at most m here. So this is smaller than C times m plus n over 2 plus 1 here. And it's not hard to see that this is smaller than C times m plus n. And actually for the last term is C times m minus Q plus n over 2 plus n over 2 plus 1. This is actually smaller than, at most C m plus n over 2. C times m plus n over 2 plus C plus n over 2 plus 1, and this is actually equals to Cm, plus C plus 1 over 2n plus 1 smaller than C. So basically this finishes the calculation. Okay, so any questions about the space complexity here? Basically, the space complexity is at most m plus OF m plus n. So we want to be a little bit cautious here. So we say that if we only want to return the value, if we only want to return this optimal value here, the space complex, you just check, for instance, whether m is smaller than n or m is larger than n. For instance, say m is smaller than n, then you just go with the columns. And if m is larger than n, you just go with the rows. If we only want to return the optimal value of the sequence alignment, the surface as a space complex is mean of Mn here. But actually, if on the other hand, you want to output like an optimal solution here, I think basically, or here basically, I'm saying this is O of m plus n. Or another way to see this is the space complex of outputting a shortest path, or putting like or returning like an optimal sequence alignment is O of max of Mn here. Because really, you need to take a look at all of this, and basically the length. If you consider, basically like a path here. If you actually need to output like a path like this, I think the length of the path should be at least larger than m, larger than m, and actually also larger than n here. So basically, the length of this path length should be at least a max of m and n here. But nevertheless, I mean, basically based on this induction, we can clearly see that O of m plus n is actually going to work here. I mean, as we can make the final conclusion, like output and optimal sequence alignment takes OMN time, and very importantly, OM plus n space. Okay, so basically this finishes the discussion of the sequential alignment problem in general about the time complexity, the dynamic programming idea, the time complexity, and also a way that we can improve the space complexity. And actually, this is a very important showcase that for a lot of dynamic programming algorithms in practice, people also use similar ideas to improve the space complexity. And also, there is an idea behind this that maybe we can combine the dynamic programming idea and also, for instance, with the divide and conquer, and maybe for in other cases, and also with other algorithmic ideas that in general really works well. Okay, so I guess this is probably a time to collect questions for the sequence alignment problem if you have.
So we just want to recover the best solution. In the original algorithm, the minimal space complexity will be OM.
Yes, yes. So basically, I mean, I should probably make this more explicit. I mean, using the original algorithm, I mean, it is very easy to see. I mean, just using this algorithm, just using this sequence alignment algorithm, the time and space complexity is O of M. So I think, for instance, in a weighted interval scheduling problem, we have this Qt algorithm just find solution. You just, I mean, if you have this whole table of M, you just like check the place whether, for instance, you have this, whether this point is actually going from this or this or this. You're just like using this find solution idea. And basically, it is very easy to see that the space complexity of outputting a shortest path is actually O of M. But actually, there is a clever way that we discussed here that the space element can be improved to O of M plus.
So is it because it's a two-dimensional structure and weighted scheduling is one dimension? So we need more space to store the internal battery thoughts.
I would say like this. I mean, for the weighted interval scheduling problem, it is a one-dimensional problem. I mean, it only has one parameter, so there is relatively little that we can play with that. But here, it is not only a two-dimensional problem, but it really enjoys strong symmetry. So that is typically a situation that people want to, for instance, like somehow, I mean, typically people say this is like a decouple of different parameters. I mean, in the worst case, I mean, you just multiply everything in dynamic programming. It typically gives you an algorithm. I mean, it is, I mean, this is not so, I mean, rigorous, but actually in a lot of dynamic programming-based algorithm, typically the cost complexity can be controlled by multiplying all the parameters. I mean, for instance, as clearly you can see here, it's basically because the array have this size of Mn, and basically the cost is just at most this. But actually, I mean, especially for high dimensional problems, maybe there are better ways you can decouple the dependence of the dimension. I mean, this is typically, I mean, especially actually this kind of idea, I mean, decoupling space is not only useful in theory, but also in practice, people do that. But it really saves a lot of space. Theoretically. Any further questions? Okay, so if there is no question, let's go to basically the remaining topic that we want to talk about. So I think at the beginning of my lecture note, I was listing both the shortest paths and negative cycles in a graph, but actually they are closely related. So let's actually begin with the shortest path. I mean, actually, shortest path is really a popular word. I mean, for basically for the sequence alignment problem we have been seeing, I mean, this can also be interpreted as like a shortest path problem, though on a very specific graph. And actually, in earlier part of this course, we actually talk about like a specific shortest path algorithm, the Dijkstra's algorithm. So I think we want to note that basically for Dijkstra's algorithm, it is a directed graph, and basically the weight of all the edges actually at least are non-negative. So basically, as maybe I can also recap here. So actually, when we studying greedy algorithms. We have learned. Digits algorithm. For computer edges, for computer shortest paths. On negative weighted direct. So, I mean, here there are basically two emphasizes. I mean, basically non-negative weighted directed graph. So I mean, directedness is basically an intrinsic nature of the graph. But actually, when we want to think about the shortest path problem, maybe we want to think about, I mean, for instance, whether we can release this non-negative weighted assumption. That what if there are some edges that actually have some negative weight? I mean, this is definitely some scenario that we want to be careful. I mean, here, I mean, the question as we are going to ask here. What if some edges have negative weights? So in this case, in particular, does Dijkstra's algorithm still work? The answer is not. So basically, on Dijkstra's algorithm, it actually will fail. So why is this the case? So let's, for instance, take a look at this very simple graph. Maybe you have an S and T here. We have one edge here. I mean, for instance, the cost is like 2. There can be also maybe two other vertices. So maybe there is a 1, there is a 2 here. So maybe this 3, this is, let's say, 2, and this is, say, -4. So if we only run the Dijkstra's algorithm, it actually directly gives ST with cost 2 here. If there's like, for instance, in this example, we directly have an edge between S and T here. But actually, S21 to 2T, 2T actually has cost, which is 3 plus 2 minus 4 actually equals to 1. And actually, this is cheaper than actually using this the call of Dijkstra's algorithm. So this is just saying that a Dijkstra's algorithm is just not going to work for graphs actually if there are some edges with negative weights. So maybe we want to think about how we can actually fix this. I mean, there are some. I mean, there are typically some brute force way. I mean, for solving the case where maybe you want to move to a negative weights. Maybe, for instance, you can just think about the case whether maybe let's see how to fix this. The first idea is that maybe we can just, I mean, if there are some negative weighted edges, we just plus some weights here. I mean, we can maybe think about this. So like a first idea is to add positive constant to every edge. I think the main issue for this is that basically you don't know the number of the number of edges on the shortest paths. I mean, it can be, for instance, the length is 2, or maybe it's the length is 3. If you add a constant here, I mean, for instance, if you the constant C here, you don't know you should, for instance, take like a 3C down here, or maybe like a 2C down here. So basically, this also actually fails. I mean, this is probably a main issue along this because paths have a different number of edges. So maybe let me finish this. So we have an S and we have a T here. So maybe we can have a graph like this. So maybe this is like 3 minus 3 here. So we can clearly see that this is actually a shortest path. I mean, in the current discussion. But what if, I mean, for instance, we just, I mean, we just, I mean, here the minus the negative egg has weight minus 3 here. So maybe, for instance, we just add 3 to all of these edges. I mean, and that is basically going to give you something like a 6, 0, 6, like a 5 or 5 here. So you see, a main issue is that basically adding the value, it actually intrinsically changes the shortest path. Basically, the top is actually the shortest. And this is basically a main issue that probably just adding like a constant to positive constant to each edge is not going to. Okay, so let's continue. Let's take a break and continue to discuss how we are actually going to solve this current problem.